The motion commotion activity really focuses on physics, particularly the physics of momentum and motion. But we're going to be focusing not on the physics of the experiment today, but on the skills that you need to facilitate that experiment. And we will talk about what Click2Science can do to help support you and your staff in being as effective as they can in leading that experiment. You can purchase National Youth Science Day kits from 4-H, and they have the cool green car that you saw me demonstrating a little bit earlier and the supplies that you need to do the experiment. They also have put together a really nice video that shows what that experiment looks like and how to facilitate it. We're going to view just a section out of that video and talk about it. As we watch the video, I want you to pay attention to the questions that the facilitator asks. We are looking for questions that ask learners for an explanation. When you hear one of those questions, go ahead and type it in the chat. We're watching about 1.5 minutes of the video, so you're going to have to pay attention in order to do that. Melissa, can you start the video for us? So look for questions where the facilitator is asking the learners for an explanation, and share those in the chat because we're going to use those for an activity in just a little bit.
So let's set up the ramp for rolling the car. Make sure that your ramp is 8 inches high, so it's 20 centimeters in case you wonder. Okay, take the ramp material and roll it out over the books and onto the table. Make sure that you tuck the edges of the ramp material into the books to secure the ramp. Hey, let's make a clay figure that will drive the car. Your kids can be as creative as they want with this. Okay, oh, it's a whole family. All right, cool. At the bottom of the ramp, there will be a book or heavy object. This is what the car is going to crash into. Here we go. Now let's place the car at the top of the ramp and hold on. Ready? Let it go. What has happened to the clay figure and to the car? Tell me what you guys just saw. Did the car travel after the crash? If it did, how far did it go? Did the obstacle move? So what's the distance our clay guy traveled after the crash? Did the physical factors affect the car's ability to stop? Was speed a factor? Before we make any assumptions, let's replace the textbook with the tissue box. Now we're going to do the same exact steps to start. So let's go ahead and take our car and bring it up to the top of our ramp. And go ahead and drop it. How is the outcome different than our first car crash? Did the physical factors influence the car's ability to stop? Was speed a factor? What happened to the driver? What is the difference between the car hitting the textbook or the tissue box? What might have happened to a person in both these car crash examples?
Give you a minute to finish typing your questions. We still need a couple of more questions for the activity we're going to be doing. Now I'm going to be adding some questions now to these discussion boxes, and what I would like you to do is think about how you think a third grader might respond to that questions.
So while you guys are typing into those boxes, I am going to talk a little bit about the questions that you heard and explain a little what an explanation is. So what were the questions you heard that focus on developing or expanding an explanation? In general, I think we think of explanations as answering why questions, but we also often include excuses or cop-outs as explanations. So kids often try to explain their way out of trouble. I'm sure we're all familiar with teenagers and other kids trying to get their way out of trouble through an explanation. But when we're talking about scientific explanations, we're looking for statements that clarify an observation or understandable. So the explanation will answer why questions if possible, and it is based on fact, evidence, observations, or patterns. So there's a handout that you can download from the file pod that gives you more information about what makes an explanation and how to explore explanations with your staff or a group of volunteers or youth leaders, whoever is going to be helping you out with the National Youth Science Day experiment. But here is the bottom line. So science requires that an explanation is consistent with observations and data collected, testable and observable in the field, in a lab, or in a mathematical model, relevant and helps clarify an issue or problem, and is reliable and supported by evidence over time. So now Sandra is going to use some of the explanations that the group shared to model how to develop explanations with you.
Before we talk a little bit about getting into the explanations, I feel like I have to refer back to one of our other skills of asking purposeful questions and comment just a moment on the questions, because we're having a struggle with some of these questions, particularly the question, was speed a factor? Because as Greg pointed out, the answer to that question is yes, and it doesn't prompt greater thinking. It was a purposeful question, but it may not have been the most well-designed question. And so I'm encouraging, and Bonnie's got some ideas about how do we build on that question, how do we make that a question that really gets to an explanation. So I want you to take a moment, if you aren't looking at those chat boxes, to look a little bit about at how the questions are developing and the responses that we have. I've only got a couple of responses, so I'd appreciate a couple more people giving us some sample responses. What do you think a third grader would respond to, having seen as much of the experiment as you have? How would they respond to those questions? Did the density of the wall affect the crash? Or how did the speed affect what happened to the driver? Or what happened to the driver? Give me a few more responses to those questions.
Yes, Sharon, I see your question there in the chat box. That would be great to frame your questions. Like a third grader would speak and use those chat box there that are labeled question 1, question 2, and question 3 to put your responses that a third grader might give you when you ask one of these questions.
Okay. I think that I have enough responses. I encourage you to keep typing and keep those conversations going to talk a little bit about how we develop these initial responses into explanations. And the first strategy that I'm going to talk about is encouragement. Encouragement means to give support or build confidence. We have some ideas that are ideas in the making, and we want to encourage them to keep building those ideas. Let me find a good example for that. Ian wrote that the driver fell on the ground. Ian, how can you describe how the driver fell on the ground? What exactly happened to her when the car stopped? That's an example that encourages the initial response, but also gives them a little bit of support to dig deeper, because what I'm trying to do there is encourage Ian to give me some more specific observations about exactly what happened to that driver. So I'm going to offer a little bit of encouragement and prompt Ian to think just a little bit more and give me more detail in his response. Now, another strategy that I think you'll find useful is questioning, using questions to guide the thinking. And that's the strategy that first appeals to me to use with question 1. Because in question 1, we're using some science vocabulary that we think a third grader might not understand. So the question was, did the density of the wall affect the crash? And then our first response is, well, what's destiny? What do you mean by destiny? I can't even say it. Density. There we go. So how could we use a question to get at that a little bit more deeply? So I might say, the book was, did the book or the box of Kleenexes stop the car faster or better? When we get to that response, then we can ask, as Greg suggests, well, what's different about the book and the box of Kleenexes? Why do you think the book acted differently than the box of Kleenexes? And when they know what the difference is, then I can introduce, through my questions, I've gotten to that particular attribute that I want to focus on. Now I can introduce the vocabulary to go with that and have an understanding that's their understanding of what density means, rather than having to explain it and try to give them my understanding. The third strategy I want to talk about is facilitation. As you facilitate, you're allowing the learner to experience, discover, or practice on their own. So with the question, was speed a factor? Well, that started out as a yes-no answer. So then the next suggestion might be, how did speed affect what happened to the driver? Another response using questions might be, what could we do to change how fast the car is going down the ramp to see if it makes a difference? Hopefully, you'll get responses along the lines of changing the height of the ramp, if some kids understand that relationship right away, or giving it a little push to get it to go faster down the ramp. Either of those responses is fine, and will again help them to explore a little bit the impact of speed on their observations, and focus them on the attribute you want them to talk about and to think about. So your facilitation is really directing them to think about the particular attribute of the experience that you want them to focus on in their explanation. A single explanation from a third grader is not going to include density and speed and what happens when the car stops. It's going to include one of those factors that we want them to focus on, that particular attribute, and give a deeper explanation. The fourth strategy that I want to include is support. As you support their ideas, you are building their confidence in the idea they've initially shared, and then promoting their interest and providing them the basis to explore that in a little bit more detail. And that's very similar to the example I showed at the beginning with encouragement, where you restate their initial idea and then build on that. I'll use question 2. So to support that idea, I would say, Bonnie, I think you've got a good idea there. We could control the speed. What do you think would happen if we did that? And then I get some more response, and maybe, Bonnie, you'll tell me what you think would happen if we tried to control the speed. So then we can keep that conversation going a little bit more. Have Bonnie show me instead of telling me. That's a good idea, Greg. What I want to explore before I go too much further in what I'm going to say is to find out if Bonnie thinks we can make the car go faster, or if Bonnie thinks we can make the car go slower. We can go in either of those directions, and I want Bonnie to be the one who decides whether we're going to try to make the car go faster or whether we're going to try to make the car go slower. So I want to support her idea, and I don't know yet, as I'm looking at her initial response, whether she thinks that she can make it go faster or slower. So you want to try to explore what they're thinking about a little bit, and then support them in continuing that line of thought. So if we think we can make the car go slower, first I want to find out, what do you think is going to happen if we make the car go slower? Then we can try it and get an explanation of what they observed, what actually did happen. The last strategy that I want to include is modeling the science and engineering practice. So I want to help them understand how a scientist thinks about the concept that they've talked about. And I have to admit, we have some good ideas going on density, but I don't really want to explore that in too much from a modeling perspective, because I'm not sure that I've got my understanding of density down. I know there's some resources in the facilitator's guide that I didn't look at before we started today. I'm not sure I want to talk too much more about density, so I'm going to keep that from the perspective of the learner's definition. But I feel pretty good that I can explore a little bit more Ian's idea about what happens to the person at the end of the drive, and think about that from a modeling perspective. So I'm going to choose the idea that I'm more comfortable with to model the science and engineering practices, and think about the idea of momentum and introduce that, and think about some real-world examples where we might have experienced momentum, where the students might have experienced momentum, and get them thinking about and making some predictions about what's going to happen when the car moving down the ramp is suddenly stopped, and why that might happen. So we're going to start building an explanation of what's happening there. So those are our 5 strategies that are going to be helpful for you as you're working with an experiment like this. Whoops, I'm in the wrong spot. There we go. To give a more well thought out, more well-developed explanation, because initially we're going to start with a pretty simple idea, and these strategies help us to encourage youth to build the idea that they're starting to understand based on their initial experience, and take it to a deeper level by prompting them to continue thinking and adding more detail to that explanation. And again, the strategies that we just talked about are in the Exploring Explanations resources in the files to download. I'm going to turn it back over to Melissa to share the next idea that we wanted to talk about.
So since we've now talked about those strategies to help learners think deeply and expand their explanations, we're going to move on to connecting prior knowledge and experiences. So if we can't help our youth connect with what they're doing after school or in a workshop, with what they do in school and what they see on TV and what they do at home, then we are empowering them to see themselves as someone who does science all the time, not just in science class. So we want to make sure that we're connecting everything that we're doing with something that they would already know or have experienced. So I want you to think back to the experiment with the car, and in the chat box I want you to type some comments or responses to this question. What is in that activity itself that makes STEM relevant to youth's daily experiences? And so what did you see in the activity with a car rolling down the ramp and hitting the books that makes STEM relevant to youth's daily experiences? And Danielle has a great comment there that most youth ride in a vehicle every day. so they have that common knowledge and experience of riding in a vehicle. And you're right, Greg, any type of collision. And we hope that car crashes aren't something that they experience daily, but many may have been in a fender bender or a car crash, and they could relate what they see in the activity back to that. Excellent, Joanne. Yes, riding their bikes, and if they've ever had to stop suddenly or quickly. And yep, coming to a stop at a stoplight or a stop sign, these are all great responses. So now we're going to go back to the video to see a little bit about how that facilitator connected the activity for his learners. There's a second experiment in the Motion Commotion activities for National Youth Science Day, where learners investigate reaction time and how distractions can change our reaction time. In their discussion, the youth are going to connect those two experiments together. And so Sandra is going to find the exact point in the video that we want to start you at, and we will go ahead and watch that second Motion Commotion experiment, and then we'll talk a little bit more about connecting to prior knowledge and experiences.
We focus on a car in motion. Now, after part 2, we have a better understanding of reaction time. These same principles apply not just to the experiment, but all around us. Imagine walking, driving, or catching that baseball. If you're distracted, you won't be able to stop your car or catch that baseball in time. Now, I'm sure you can name a bunch of examples where distractions affect your role in the physics of everyday life. And sometimes it can be really dangerous. Let's call out a few of them.
Texting and driving.
Texting while you're walking.
Putting on makeup and driving.
Listening to music while you walk. And talking to your friend while you're biking.
Yeah. Now that you guys understand the physics of motion and reaction time, you can actually play a role in your community by being aware of the distractions and keeping everyone safe.
Again, I forgot to unmute my microphone. Sorry about that. So I want to point out a couple of things about connecting. In the video here, the facilitator is using this discussion about making connections to wrap up the activity and tie the two experiments together. In the activity guide, you'll find resources for helping you take action based on what they've learned. As you support them in making connections to their own life and taking action, you're empowering them to understand how science can help people and change lives. You're helping you see themselves as someone who can help others. This is powerful stuff for young people, especially in upper elementary and middle school, where they are starting to see themselves as independent. Another way you can use this skill is at the beginning of an activity. We didn't show the first part of the video today, but it starts with some real-world examples of motion, like bumper cars. You can engage youth in these experiments by starting with what they already know. When you demonstrate that you value what they already know and have experienced, you're reminding them that you value them as individuals. That is important. We want the youth in our program to feel valued each and every day. We want them to know that we see them as knowledgeable and that they have something important to share with the world.
Can you advance it? Thank you. All right. So what we've tried to bring together here today is how you can help prepare the staff in your program to help learners develop and expand explanations as they're doing a fairly simple activity. And also how you can connect that experience to their prior knowledge and prior experiences so that you can help make that activity more meaningful to them and the learning something that's going to be more useful for the students. So what we want you to understand is that we're really looking at two different skills here from the Click2Science website and how these skills connect to this activity, motion commotion. And we want to make it clear that you can download the motion commotion experiment guide from the box below and pick that up, and you can use it just as it is with your program, or you can also go to the National 4-H website and see how to connect to the National Youth Science Day. Greg asked if there's a model explanation connecting the two experiences. As you download that experiment guide, you'll find there's a lot of resources that help you build the background on the science content that they're covering in the experience, and also help connect those two activities together, and also take it to the next step, because what they do in the activity guide is you connect the activity the students did about reaction time to the experiment they did about motion and momentum, then that leads to discussions about distractions while driving. And there are also a lot of resources that you can make use of on distracted driving that bring those two ideas together. There's also resources to help you take it to the next step, to help them apply what they've learned by being active and doing some service learning in their community around these issues of distraction and driving. The learning modules that we used in the workshop are ones that you can download from the Click2Science website, and we selected these particular resources because they make it easy to introduce these ideas around developing and expanding explanations and connecting to prior resources. And that seemed particularly relevant to this experiment. As you prepare your staff to do this experiment or to participate in National Youth Science Day, we also want to encourage you to use these training resources to help build their skills so that they understand the science behind it, but also the facilitation skills they need to really make that a meaningful learning experience and to deepen the learning for the children in your program. I want to share with you some resources you can use to connect to us and can keep this discussion going. And we're going to open it up for some questions now. And I see there are some questions.
Yep, excellent. So Ian asked a question about the National Youth Science Day experiment and what age group this is the most useful for, or it's designed to be used for. And it's designed to be used with middle schoolers.
Upper elementary and middle school. It is intended for upper elementary and middle school age use. I think I recommend about fourth grade, but this activity I think could be used with younger students.
And I think it's especially relevant to middle schoolers because I know if you work with middle schoolers, all of them have cell phones now. And so it's a good discussion on distracted, texting while walking, texting while riding your bike, any kind of that distraction that can affect you. And so Sharon has a question. I think Sandra would probably be better to answer this question.
Oh, I actually have the answer to that. The kits are $23.95, and they come with 2 cars, and the one ramp that I'm using is 4 foot long. They recommend cutting that into 2, so you would have 2 2-foot or 24-inch ramps, 2 cars, some clay, and you get, I believe it's 5 of the learner guides and 1 facilitator's guide in that kit. The cars are just adorable, so I would recommend that you look at the kit because they work really well because they're open and the clay comes out of it pretty easily.
And we will continue to take questions, so if you want to type those in the chat box.
There's a question from Greg about how these experiences are tied together. And as I mentioned earlier, they use the concept of distractions while driving to bring these together. And here's kind of a summary at the end of the guide. It says, we observe that both physical and human factors affect our motion. Based on our observations and discussions today, what actions can we take to improve our safety? And then it has several facts about distracted driving, distracted walking, or cycling, and then and about the brain itself, and then some actions that you can take. So the idea is to start with their experiences, to build their knowledge through the experiment, and then take it to that next step of action.
And so we've got some questions about what day the National Youth Science Day is and how you order kits. I just posted the website for National Youth Science Day there in the chat box. And so you click on that link or copy and paste that link, and then you can register and order kits from there. We also had a question about which day National Youth Science Day is. Perhaps, I'm not sure exactly who said the wrong date, but it is October 7th. So that's the day we're going to have a Twitter chat, and so pay attention to us on Twitter, and also definitely do your National Youth Science Day experiments and post pictures and any comments that you have from that. So Greg has a really great question about transitioning from crashing cars to catching a ruler, and how to best support volunteers in making the shift.
And that's not going to make sense to people who aren't familiar with that experiment. So let me demonstrate. We've got a minute. Let me demonstrate quickly that second experiment. I was using my ruler to give my ramp a little bit more strength. The second experiment has them hold a ruler in their hand and then test how quickly they can catch that ruler. And then you add the element of distraction and look at how the timing to catch the ruler changes. Transitioning is going to be awkward. And in the guide, it simply recommends that there's experiment 1 and experiment 2. You don't try to transition from one to the other, but then you use the discussion after the second experiment to tie them together. Are there any other questions? Well, we have a few more minutes to spend with you.
So I've been responding to Holly's questions here in the chat box, but I'll go ahead and say that out loud so we have it recorded and everybody can hear it. If you want to go rewatch this webinar for whatever reason, it will be listed on our website. It's on our events page under our on-demand webinars. So you can go there and also check out any of our webinars from earlier in 2015. We've got a lot of great ones about asking some purposeful questions and sparking interest in STEM, and we've got one from Digital Learning Day that was really great. So we encourage you to go check out those webinars to get any kind of on-demand professional development that you may need and to learn a little bit more about Click2Science.
Melissa, what do you need to do to follow us on Twitter? Because I forgot to put the Twitter link on our slide here.
So we are at Click2Science.
Okay.
Is our Twitter.
I remember. Thank you.
Excellent, Sharon. I'm glad that you have a Science Sundays, and hopefully you find the Click2Science resources beneficial as you get your staff geared up and ready to go to help those youth engage in STEM.
And Greg, I'm going to respond to your question before we wrap up. There's a lot of information in the guide that really helps bring the physics to a level that our staff can understand. It is pretty basic, but it gives them enough of a background to be able to use the vocabulary and be able to explain it in a way that we think is going to make sense to the learners as well as make sense to them as they're facilitating the activity. The best preparation to do with your staff is really to do the experiment together with them before they have to do it with children. That's not always possible, and we understand that. But I do encourage you to look at the resources that we've shared here, the full experiment guide, and also the full video. We just showed you a couple of short clips out of that video because of time in the webinar, but it does give you a good overview of the whole activity, how it connects together, and some of the basic science. So I recommend you go back to the guide to really get a good explanation of the science that's behind the experiment there.
And we do want to encourage everyone today, if you are not already registered, to register at the Click2Science website so that you have access to all of our resources, activities, and post comments on the learning module, and subscribe to our email list so that you can know about all of these great webinars. We have another one coming up on September 23rd to help you connect with community partners for your Lights On After School event. So please join us for that one. We'll be having webinar Wednesdays at 1 o'clock on a Wednesday during each month. So obviously the date will change just because there's not one Wednesday every month where we're all available, but keep your eyes open for those in your email, and we hope that you join us for some future webinars. I don't see any more questions coming through. So if there are any more questions, please hurry and type those in. Otherwise, we'll go ahead and wrap up here today so that you guys can get back off to your busy lives and schedule.
If something comes up later and you think, oh, I wish I'd asked that, please email us. It's really easy to remember, Click2SciencePD@unl.edu. We'll be happy to respond to additional questions there.
Thank you so much for joining us today. Just once again, our next webinar is September 23rd, Connecting with Community Partners for your Lights On After School event. So please join us then. Have a great day, everyone.